I'd like to introduce one of our premier researchers who has been doing some extensive work in quantum physics, and he has some interesting stuff to present. Vaibhav, why don't you take it away?
Perfect. Thank you so much. So I'll just get the screen share ready. 1 second. Sorry, give me a second. Technical difficulties as usual. As I'm sharing my screen, so this presentation will be slightly different for everyone who's been attending every single one of the previous quantum physics meetings and has been looking at the same things again and again. This one is not going to be like that. This one's going to be different, don't worry, because we are actually doing something that was actually, we didn't even know that it was, we could even come to this state at the moment, but now we were able to actually, we have some very exciting information and updates, and we are actually quantum computing and quantum chemistry, formerly called quantum physics. We are actually launching a collaboration project this semester onwards, and today we're going to be doing a joint presentation on updates within both of these projects. And of course, my name is Vaibhav Ayakarnam, and quantum chemistry leads.
I'm Adelina Chow.
Hi, I'm Max. Don't try pronouncing my last name.
And I suppose
maybe you should each say which of the projects that you are focused on.
Yeah, so for me, I'm focusing on the quantum computing aspect of the project. So yeah.
I am also focusing on the quantum computing aspect.
Max and Adelina are the coordinators of the quantum computing group, and I'm one of the coordinators of the quantum chemistry group. And so without further ado, because we are two groups presenting in the time of one, take it away.
So what exactly are we researching in the quantum computing group? So essentially, our group focuses on researching quantum generative adversarial networks, which are an unsupervised learning algorithm that can discover valid drug candidates that abide by the laws of physics and chemistry. So why this generative adversarial network, right? So essentially, this machine learning algorithm works very efficiently with complex data and can also be trained with missing or incomplete data, which is perfect for our research. However, there are a few problems with this generative adversarial network, which is a vanishing gradient problem and the increasing algorithmic complexity. Furthermore, there have been fairly limited unsupervised learning applications in the field of chemistry. However, there is only one, and that is the qGAN, which we will further go into detail later on. So for our research project, the main goal is to develop a generative model that can essentially learn the representation of molecules more efficiently than a classical machine learning model by searching the exponentially large chemical space.
Okay, so what are GANs? GANs are short for generative adversarial networks, and they are a machine learning algorithm where two networks, a generator and discriminator, compete against each other to generate an object, such as a molecule in our case. This relationship between the two networks can be described by the image to the right. The generator is like a fraudster trying to manufacture counterfeit money to fool the discriminator, while the discriminator is a detective who is trained to classify sample money as real or counterfeit and prevent the generator from committing a nefarious amount of tomfoolery. Because of this architecture, GANs need a unique training process in order to simultaneously train both networks. So here's a simplified version. In each epoch, the generator generates a fake object and gives it to the discriminator. The discriminator decides how real the fake object is and compares its decision against the actual label of real. It then uses this feedback to learn how to better classify objects as real or fake. The generator uses this feedback to get better at generating fake objects. This repeats until the discriminator is immune to the generator's trickery and the generator is unable to become more nefarious.
So as I mentioned previously, there's only one significant breakthrough for using GANs with chemistry, and that is the MolGAN. So the MolGAN has been proven very successful in generating synthetic and chemically stable molecules. However, we found that the MolGAN could be improved upon by leveraging quantum computing. So what exactly is quantum computing? Essentially, quantum computing is the art of using harnessing quantum mechanic properties to essentially perform like computational tasks. So quantum computing is able to process high dimensional data really efficiently, and it harnesses quantum mechanic principles such as superposition entanglement, which we are able to use to our favor. Furthermore, there is also very low memory usage on quantum computers, which is because of qubits, which decreases computational resources significantly. Thus, we propose the quantum GAN, or which we will be referring to as the qGAN. Our qGAN has a quantum generator and a classical discriminator. And the reason being for this is we noticed that the generator would be using more computational resources since it has to actually generate the molecules, which is why it uses quantum computing. On the other hand, discriminator will just be a simple classical model because machine learning libraries have been very much optimized in the classical computing world, which is why we went with this architecture. Later on, the qGAN is trained on the QM9 dataset with 134,000 molecules in the XYZ representation to generate synthetic chemically stable molecules.
Okay, so there are 4 parts to our qGAN. There is a dataset loader, a generator, some post-generator processing algorithm, and a discriminator. So the QM9 molecular dataset provides the discriminator with the real examples of valid buildable molecules, which are conveniently stored inside the dataset loader, which loads the dataset. Since the molecules from the QM9 dataset are represented in the XYZ file representation, the dataset loader also helps convert these files into CSV files for ease of use. And then we'll visit the other qGAN components after we get more acquainted with our new friend, the QM9 dataset.
So essentially, we trained our qGAN on the QM9 dataset, which Max just mentioned, and this dataset has approximately 134,000 organic molecules having up to 9 heavy atoms. The term heavy simply refers to any non-hydrogen atom. And by the way, the different types of elements that were in this data set were carbon, nitrogen, oxygen, hydrogen, and fluorine. However, we did not use any molecule that had fluorine later on. Originally, we tried to use the simplified molecular input line entry system method, which is also referred to as the SMILES method to encode molecules. And this is also the representation that the QM9 dataset originally comes in. This method of representing molecules would encode several molecules' spatial features, but this typically faces issues in machine learning due to its complex grammar, especially when it comes to generative networks. Furthermore, the strings would have variable length, which would make it very difficult for our generator to generate similar molecules. To mitigate this, we decided to use the XYZ representation format. Next slide. Okay, so essentially the XYZ file format encodes the molecular geometry and the 3D structures of the molecules. It stores the list of atoms in the form of an atom vector with corresponding X, Y, and Z coordinates of each atom. Prior to passing these XYZ representations into the qGAN, we converted the file type from XYZ to CSV, which simply just refers to changing the file extension. We did this to make it easier to work with the data in Jupyter Notebook. Our quantum generator generates molecules that mimics the XYZ file format by allocating a set of qubits for generating the respective part of the XYZ format. For example, we have a set of qubits to generate the atoms, a set of qubits to generate the X coordinates, a set of qubits to generate the Y coordinates, and last but not least, a set of qubits to generate the Z coordinates. In total, we use 20 qubits with 1 extra. However, we are able to generate 4 to 20 atom molecules now because we have upgraded our output processing algorithm so that it is more efficient in using the bit string. In the future, we would also like to utilize 32 qubits and then 65 qubits, as well as to run the qGAN on a real quantum device and not just a simulator. After we finished generating all the molecules, we tried to check the validity of the generated molecules. To do this, we would convert the XYZ representation of the molecules back to the SMILES format. Since Smile's string follows a very specific grammar rules with different types of bonds corresponding to different symbols, parentheses to indicate branches, and numbers to show rings, invalid molecules would not have a valid Smile string. As a result, any generated molecule that has a corresponding valid Smile string would also therefore be a valid molecule. So here's just our code for the dataset loader.
Okay, so onto the qGAN architecture. This is the real deal now. So the generator is a model that generates fake molecules. It consists of a series of parameterized quantum circuits, which are shortened to PQCs. These are quantum circuits with parameters. In our case, these are rotation angles of rotation gates, and they control how the input is transformed into the output, and can be thought of as a quantum equivalent to a classical convolutional layer. These parameters are trainable and can be adjusted via a feedback loop and an optimization function. We use superposition by performing the Walsh-Hadamard transform and also achieve linear quantum entanglement with the controlled rotation gates. By repeating layers of superposition and entanglement, we allow the generator to become more accurate. And finally, the quantum state of all the qubits is measured on the Z basis via poly-Z measurement gates, which results in a bit string, and that needs to be converted into a meaningful vector that will represent a molecule. So for this, we have a quantum analog to digital converter, a QADC. It outputs numbers of greater resolution. The resolution, by the way, just indicates the number of possible discrete values over a certain range, and a greater resolution would require more qubits. So once the QADC processes the output of the quantum circuit, it is exported to the discriminator as a CSV file. The discriminator uses the CSV file to perform the simple task of two-class classification compared to the generator. It's basically a neural network. Yeah, okay. This is the generator. It's the main component of the qGAN, the one that does all the heavy lifting. But it's surprising to know that the input to the generator is actually just a bunch of random noise drawn from a uniform distribution between 0 and 1. Very unexpected. How can such chaos create order? Well, we have PQCs for that. As mentioned, we have Hadamard, CNOT, and rotation gates to apply a bunch of superposition and entanglement to the qubits and map them from their initial 0 state to their final state, which we measure in the Z basis. As we said, this gives us a bit string, which represents a molecule, and it is inputted into the QADC on the next slide. After this bit string goes through the QADC and the discriminator, the generator finally learns how realistic its output was and optimizes itself by adjusting the rotation angles using an optimization method called the parameter shift rule. Okay, next slide is our code. Very amazing. Okay. And now the job of converting the bit string into a meaningful representation of a molecule is a job for none other than the QADC. It reads through the bit string in chunks of information representing one atom each. This chunk of information is transformed into 4 entries, the symbol of the atom and the XYZ coordinates. You can see an example of this at the bottom. The coordinates are calculated by converting the chunk from a binary integer to a decimal integer, and then dividing a number which just happens to be a power of 2. So for the example on the bottom, we give the QADC generator output, and it returns the 4 previously mentioned entries. The atom symbol is a float, which we convert to an int. We have to use the int instead of a string because the code complains if there's more than one data type in the tensor. However, we have a dictionary in which each int maps to a unique atom symbol. So 1 represents hydrogen, 2 represents carbon, 3 is oxygen, and 4 is nitrogen. And although QM9 dataset also has fluorine, we don't use 5 to represent fluorine because apparently we hate it. Next slide. Okay, so finally we have the discriminator, which is the critic responsible for updating both itself and the generator. Not that, like back. Yeah, there, okay. As an input, It first trains itself on an example of a real okay, no, like previous. Bro.
One
Yes.
second, sorry, technical difficulties. There we go.
Okay, no worries. Okay, so anyways, the input is an example of a real molecule from the data set. So it knows what kind of trickery to expect from the generator. Anything that doesn't resemble the thing from the data set will be classified as fake and vice versa. Now we give the discriminator a generated molecule that is kindly provided by the generator, but we don't tell the discriminator that the generated molecule is labeled fake, because the discriminator is supposed to decide whether this is real or fake based on what it has learned so far. It returns 1 if it thinks the generator's output was real and 0 if it was fake. After it decides for itself, we then correct the discriminator if it was wrong and tell it what the actual label of the molecule was, i.e. fake. And it learns to become more accurate with its classifications. We also tell the generator which verdict the discriminator returns, so the generator learns how to become more nefarious and generate more realistic fake molecules. Next slide. Yes, this is our code. It is also very amazing.
Okay, so for our results, we generated 300 molecules total, and out of those, only 7 were chemically valid. And for us, we defined valid in accuracy in terms of atoms. So essentially, we just looked at the order of the atoms and instead of the coordinates, because we noticed that our coordinates were not like completely random. So there was no way for that to ever match up with the atoms. So that's essentially why we only took into account the atoms. However, in the future, we do plan on fixing these coordinates so that the molecules would be fully accurate. So in the end, we had a 2.33% success rate. Can we move to the next slide? Okay, so here we essentially have like 3 examples of our molecules. So we took some of the molecules that we generated and modeled it in Avogadro. And as you can see here, many of our molecules are not actually molecules at all, but just rather a collection of atoms randomly just around in space. Obviously, this would not be a very good drug candidate, nor is it actually a molecule. However, some of these molecules do exist, just not in the configuration shown. So let's look at the molecules from left to right, and this kind of shows a progression of how the qGAN kind of gets better over time, right? So on the left, we have C3H4O2N, and it really is just all the atoms kind of just scattered around in space, and we tend to like just kind of like give our atoms names. So we just kind of call this on a scatter plot because it's literally just randomly scattered around. The one in the middle is C2HON. However, as you can tell, there is improvement, as in there's 1 OH bond now. However, it's obviously not good enough to be a molecule. And last but not least, on the very right, we have C3H2. And as you can see, we now have 2 bonds. So as you can tell, you kind of can see the progression of the generator kind of slowly getting better over time and bonds being able to form. Yeah, we can go to the next slide. So drug discovery is typically a very long process that takes many, many years, but it can be made a lot more efficient with the flexibility of our qGAN. The data set used to train it can be varied to generate molecules with certain chemical properties, such as polarity, conductivity, and the functional groups deemed necessary for the potential drug candidates which are targeting a disease. In doing so, our qGAN would produce the most viable drug candidate specific to a target disease, reducing the number of potential molecules to be screened and making the molecules generated by the qGAN more likely to be feasible. And this typically just like expands the amount of like drug candidates that we screen and ensures that these drug candidates are actually have potential to be viable. So that's kind of the point of the qGAN. In addition to drug discovery, our qGAN is applicable to a variety of other fields, including material science, where new molecules can be used to develop novel materials, solar energy production to develop low-cost organic solar cells, and agricultural production to discover new methods of pathogen control.
Okay, so future work. The future is looking quite bright for us. Because we realize that molecules are like mini graphs, we are working to transition our generator towards becoming able to generate graphs instead of just a bit string. This is because our current molecules, as you can see, are just atoms vibing around in empty space doing whatever, which should not make them great molecules. By switching to graph-based qGAN, we can ensure that the atoms actually bond to each other. And in addition, some of our molecules do not satisfy the octet rule and have insane formal charges of like -10. So we're working to enforce these rules and make sure our molecules are more reasonable. We also need to upgrade the discriminator so that it can work with generated graphs. And we've also been doing some research on loss functions, and we plan on switching it to something called the log p score on the right, described on the right, which is commonly used for molecular generation modules. And since we're using graphs, we might disable the QADC since it doesn't look very helpful anymore. We also plan on simulating the generated molecules and evaluating them for their potential success using drug likeness analyses techniques like Lipinski's rule of 5. Oh, that's a tongue twister. This rule would determine whether a chemical compound has the physical and chemical properties to become an orally active drug. After our generator transitions to being graph-based and we confirm that the thing actually works, we plan on generating many more molecules that hopefully are valid. We will then donate hundreds of these molecules to the quantum chemistry groups so they can use them for their own project. Vaibhav will explain.
Thank you so much. So for all of you who thought the presentation began differently for a quantum physics or quantum chemistry presentation, yeah, okay, Hartree-Fock. If you guys have been here in the last 4 presentations, this is the time to go to the bathroom, take a drink of water, whatever. But here's going to be the exact same rite of passage that's been happening before. So if you've already seen the introduction, feel free to take a break and come back when we're talking about the data. So first of all, why quantum physics? Essentially, at our level, at the macroscopic level, we use classical mechanics, which is where every object can be treated as a particle, as we would say, or a mass that moves around with a certain, as we call it mechanics. That is the study of the motion of how an object moves and why it moves. The problem is when we look at it at a quantum scale, that is at the scale of atoms, molecules, and subatomic particles, this falls apart because we find out that in the experiment that was shown, is called the Young's double slit experiment, we found out that starting from electrons, everything at a quantum level actually behaves as both a wave and a particle. So its mechanics are vastly different from how it would be in classical mechanics. That's why we have quantum mechanics. So that describes the behavior of why and how things move at molecular, atomic, and subatomic systems. And it's one of the 2 major models of the universe, with the other one being relativity. It does have some unanswered questions, but quantum mechanics is the first theory to have never been disproven yet. So I will move on to one of the main equations, one of the most famous equations of quantum mechanics, is sometimes thrown around as a buzzword, the Schrodinger equation. Essentially, what the Schrodinger equation does is it solves for the wave function of an electron within an atom. Now, the wave function of an electron is essentially the electron, different properties of the electrons, such as its position or momentum, etc., that are stored as numbers. And we call a lot of these, we call these numbers, all of them combined, quantum numbers, and the wave function provides an accurate description of all of them combined. And so having that essentially describes the entirety of the mechanics of the electron. So it'd be very useful knowing that. And so that's what the Schrodinger equation solves for. Your Hamiltonian matrix, represented by H hat in the image, that represents the total internal energy of the atom's nucleus. Psi represents the electron wave function, as I mentioned, and E represents the energy of the electron, the specific electrons we're looking at within the atom. And so for those wondering if we can cancel out the size, no, unfortunately we cannot. This is a matrix equation, a differential matrix equation. And for those of you who already know it, I'm sure a lot of you just sighed and went, not this again. But yeah, you can't cancel out the psi because it's a matrix, yeah, it's a vector, and Hamiltonian operators of matrix. You cannot cancel out the size. That's not how this works. There are only very specific values for which the left equals the right, and because of that, those distinct values, which we call eigenvalues. Those are the energies of the electron. And this is a very, very useful equation, but only for hydrogen, because when we actually move on to multi-electronic atoms, we see that since the electrons repel each other, their motion and therefore their wave function is dependent on each other. So the equation actually falls apart. So instead, we approximated using self-consistent field methods. Now, these are computational methods, like I said, that approximate the Schrodinger equation. As depicted on the image on the right, they start off with an initial guess for how the electron wave functions may be. And then after that, they apply recursive calculations to get the wave functions to be more and more accurate until you reach a converged limit for the wave function as well as the energy of the electron. That's what we call the convergence point. And there are three groups of SCFs or self-consistent field methods. A lot of the chemistry groups may already be familiar with the density functional theory methods, but we are going to be looking at a more precise version called Hartree-Fock. Before we get to Hartree-Fock, we need to talk about how the initial guess is actually done. And that's what we call a basis set. Now, our basis sets, there are different ways of modeling the initial guess that we use for the electron wave functions. Now, we actually look at the electron as a polar function, and we can model how that polar function looks like using equations. The one on the top left is what we call a Slater type orbital. Now, that's much more accurate, but that's quite slow when we actually run it as a computer program, and that requires much more computation. On the other hand, Gaussian type orbitals, which are in the middle, those are much faster, much faster, but they compromise on accuracy. So instead of actually using a Slater type orbital, we can take a Gaussian type, we can take numerous Gaussian types and add them together. For those of you who have done linear algebra before, it's not just normal addition, it's linear. We call it a linear combination, which means we take multiple Gaussian or type orbitals, add a constant, and then add them together, and then that approximates a Slater type orbital. And so the number of Gaussian types that we sum up is called the size of a Gaussian type orbital basis set. More functions means it's more accurate and closer to a Slater type, but it takes longer to calculate, and vice versa. With that in mind, we're looking at a very specific subset of the Gaussian type orbitals called the STO-nG Popel basis sets. These are called minimal basis sets because they're very, very small. And they are, the n in the STO-nG is the number of basis sets that are being summed up. They were created by John Popel. That's why they're called Popel basis sets. And we looked at 5, 2G, 3G, 4, 5, and 6, each referring to the number of electrons. I'm sorry, the number of basis Gaussian type orbitals within that set. And essentially, I'll come back to this, but we tried calculating it from. We used information for the basis sets from helium to xenon because that's what they've been calculated for. Beyond that, the basis sets are either just too small to be accurate enough for the atom, or they haven't been calculated yet because the computational power required to do so is quite large. Now, with all of that combined, now that we have our wave function initial guess, we've used self-consistent field methods, we have a converged wave function, we plug it back into a modified version of the Schrodinger equation, which we call the Hartree-Fock method. And essentially the Hartree-Fock method is we can write it in a way called the Ruth-Hall equation, which we see here. Now this looks strangely similar to the Schrodinger equation. That's because it almost is the same thing. And essentially now first we have our Fock matrix. That's going to be our Hamiltonian matrix, but also added with the sum of Coulombic repulsion. As I mentioned, the electrons are actually repelling each other. So that factor is taken as a matrix G. H plus G gives F. Then the orbital coefficient, they're all of the wave functions combined. Those for each of the electrons within an atom. That's going to be in the orbital coefficient section, which is represented by C. There is a new addition here, which is S. That's the overlap matrix. Essentially, when orbitals overlap, that is taken into account by S. Finally, we have C again, and then we have epsilon instead of E, and that's the energy of every single electron, the ground state energy of every single electron within the atom. And so with this information in mind, what did we do? Well, we wanted to calculate the ground state electronic energies of electrons from atoms from helium to xenon using the STO-nG basis sets and the Hartree-Fock method. Then we wanted to tabulate that data as atomic energy versus atomic number. tabulated, get out a graph, and after we get out that the plot, we wanted to find a regression to hopefully not only see if a regression can be used to approximate the data set, but also predict beyond xenon. So in order to look at that, first what we did was, well, first we calculated the energies using a library called PySCF, which of course, if you guys were on your bathroom break, please come back now. This is the data collection part, of course, and PySCF was the software that we use, the library that we use. It's a Python C++ library, and using that has Hartree-Fock, post-Hartree-Fock, and density functional theory methods, which are different types of self-consistent field methods, essentially. And it supports GTO basis, so there's Gaussian type orbitals, and it's very, very helpful in actually condensing our code, because we used to have a code that was 500, 600 lines, and we've condensed that now to just we've condensed that now to like 8 to 9 lines. And essentially, using PySCF, we got the data as with the code. Sorry, I'll go back. This is the code for actually calculating the energy of a certain electron. We took that and then we actually put that into matplotlib, which is a tabulating library, and that actually gives us our table, the one I was talking about, energy versus not exactly atomic number. Here it's atomic, this is the element symbol, but we changed that later. We collected it, and we did the opposite of a shortcut, and we took a long cut, shall I say. Instead of tabulating all of them at once, we actually split it up into multiple different element groups, as can be seen.
I'm gonna quit ASDRP. Okay.
Sorry. We split it up into multiple different element groups and also multiple different basis sets. That is the 5 basis sets. And we actually made tables so that the programs run easier. We were able to divide work among the group. So we ran as displayed. Those are the groups we use. And then we took the matplotlib table, which was actually in a PNG format, as can be seen on the slide. And then we put that through an OCR software to convert it into Excel. Then we took that data and we put it, and we started doing regression modeling on it. I will return to that later because that is highly inefficient. Model formulation. First, we actually tried it on a software called Logger Pro. Again, I'll come back to that. We decided for it, since it was easier to actually visualize and also just manipulate regressions with, we tried using Desmos instead. And essentially what we did was we took the table, we put it onto Desmos. First, we took just the data from helium to krypton, that is from element 2 to element 36, and we put it in, and we got out the regression. Then, as I'll explain on the next slide with a bit more data, we after making the regression, we put in more data from krypton to xenon, from 36 to 54, see how the regression correlation changed. If it changed a lot, that means it didn't predict it well. If it doesn't change too much, that means, okay, it's a good sign, because that means it predicts well and it approximates well. The first part was approximate. This is what you can see there on the table. The correlation coefficient, essentially, that's how close the regression is with the data. And so I'll return to which ones were better and which ones were worse towards the end. Then, of course, as I mentioned, we took the data, and then we added in extra data from krypton to xenon, see if the regression held. First, we calculated the new coefficients, that's being kept up there. And then after that, we calculated the difference in the new and the old coefficients before and after adding the new data. And we made another table of that. That's the second table. And essentially now for the inference is the most important part. If you were on an extended bathroom break, please come back now, because this is the actual, these are the updates here. Now we have 3 quantities that I mentioned. The first was old coefficients. That's what shows which regression was the most feasible. And for at the beginning, when starting off, all 3 regressions we hypothesized would be feasible. But we found that sinusoidal, so we tried 3 regressions. We tried the exponential, sinusoidal, and quadratic regressions. Exponential and sinusoidal just because those were actually, commonly used regressions. Quadratic because a bit of math involved, but one of the approximations of the atomic energy and of electronic energy can be written as a proportion of energy to the inverse square, or I'm sorry, energy to the square of the atomic number. So we tried quadratic as well. We found found that sinusoids and quadratics had average coefficients that were greater than the exponential regression. So that means that sinusoids and quadratics actually correlated with the data much better than exponentials, even starting off. We decided to continue with the new coefficients of determination. Now, these are the coefficients after the new data has been added. So if they talk about how good the regressions are with the new data included as well, how accurate they are. We found that sinusoidals, oddly, interestingly, we don't know why yet, that's what more research has to be conducted on, but sinusoidal regressions were the best fit, followed by quadratic and then exponential. Then we also, of course, calculated the change in the coefficients of determination to see how much the precision has changed from the initial to now after adding the new data. And we saw the same thing. The sinusoidal regressions had the lowest average magnitude of change, and then quadratic, and then exponential. So we think that our suggestion, I suppose, postulation is that out of these three, the sinusoidal ones are the best regression that could be used to model this. We did see a few anomalies that I will discuss in the future section. So the first thing is, apart from our research, like if we just want to start off anew from here, we wanted to, for future work, it would be expanding our regression plots to other SEF methods, like I mentioned, Hartree-Fock, then there are density functional theory methods and post-Hartree-Fock methods. We wanted to look at other basis sets as well, so maybe a bit bigger basis sets like CCPVNZ and whatnot. And then we also wanted to make some method improvements. Like I said, since we had a lot of delays in looking at converting it from an image to Excel and then on to Desmos, we want to improve that by including Logger Pro, which is actually a scientific data arrangement and regression software. So we're looking at investigating that, as well as other math programs for easier regression construction. The other thing we wanted to investigate was, and I will conclude with this before we move on to the future works, there were a few anomalies here. If you notice the change here, some of them, STO-4G and STO-2G, actually have very small magnitudes in the change of the precision, while STO-3, 5, and 6G have much higher changes in the regression precision. So we wanted to investigate why that was happening. Our current, we think that it was actually a problem in generating the regressions on Desmos because of a precision error. It only actually accepted around 6 significant digits of for the coefficients in the function. So that's why, again, we're looking at Logger Pro, which provides us almost 15 significant digits. And with that, now the most exciting part, unfortunately the shortest as well, a collaboration.
Okay, so essentially for our collaboration of the two groups, the purpose is to essentially improve on existing molecular property determination software. So essentially how this is kind of going to be split up is that the quantum computing group is going to be using our qGAN to generate these molecules, and these molecules are essentially going to be computed for drug likeness, and then any molecules that are deemed like potential drug candidates will be sent over to Vaibhav's group, who will then be performing these molecular property calculation stuff using Hartree-Fock. And in this way, we're essentially verifying that these molecules would be valid. And then after that, this collaboration has many potential applications. For example, molecular discovery and reaction pathway synthesis in fields like material science, organic chemistry, biochemistry, pharmaceuticals, and so much more.
Okay, so as you can see, there are two pillars of improving this method. The first is increasing precision of calculations. So what in the world does that mean? Well, you came to the right place if you want to get that question answered. So basically, right now, like all these like classical like molecular calculation like softwares, like they're not that precise as Vaibhav may have mentioned. And so what we want to do is increase the precision of those calculations by going quantum, which also helps because those software you use a lot of resources, like Vaibhav said, like they run for a very long time. And by using quantum computing and quantum computers, we can like decrease the memory usage by a lot. And also because quantum computers are just like way cooler, we want to have like the coolness factor in there too.
Quantum itself has this kind of like cool factor to it, I think. Yeah, but of course that's biased, so don't listen to me. But essentially comparing the current system with the replacement that we're proposing, a lot of the chemistry groups actually do use a similar system. Avogadro has a classical GAN network that optimizes and generates molecular geometries. And then stability calculations are performed using ORCA and density functional theory for like vibrational states and reaction pathway determination using B3LYP and other basis tests. We are going to take that and make it, like I said, more precise. And like Max had mentioned, we're going to move it quantum first to make it a quantum classical GAN, so that takes up a lesser space and while actually run times decrease and there's higher precision. And then we are going to be changing it on our side by using Hartree-Fock instead of density functional theory, and we're going to be using CCPVTZ basis sets, which are much more precise than other density functional theory based basis sets. And so we have a lot that is planned, and we're very excited to see how that goes. And first of all, we would like to, of course, credit our presentation to all of our previous group members and current group members in both quantum chemistry and quantum computing team. And we would like to also credit Dr. McMahon, our advisor, who guided both groups throughout the entire research project. We would like to thank Mr. New Edward, because he actually gave us a lot of suggestions for both quantum computing and quantum chemistry and how we could proceed from here and actually integrate this entire process. And ASDRP, who provided us a place to do the research, and also the former quantum computing leader, Diptanshu, who gave both teams a lot of advice on how we can actually string these two topics together for this sort of a collaboration. And yeah, we're finally done ranting. Any questions?
That was very, very impressive. Larry, congratulations. That was a very impressive presentation. No questions, but I just have to say that's very impressive what you guys have done.
Well, thank you very much. It was all my students' hard work. I think they did an excellent job, and I think that they did a fantastic job, not only of understanding and applying the physics to it, but they showed an extreme amount of dedication in digging out the information that they needed to be able to do this correctly. So I have a question for Max.
Yes.
Why do you hate fluorine?
Well, you know, it's very electronegative, and I don't like things that are negative.
So I will ask Edward. Edward, are there any fluorine organic fluorine compounds that have positive drug use?
Actually, a lot. This is interesting. There's a recent review in ACS-Omega by Inoue, I-N-O-U-E. If you just Google ACS-Omega fluorine medicinal chemistry Inoue, that actually describes the utility of fluorine. So yeah, fluorine is very electronegative, but the nice part about having fluorine in your compounds is it makes it metabolically inert. So if you have a compound that gets degraded in the living system too quickly, you can simply replace the hydrogens that get degraded with fluorine, and that molecule becomes, pretty inert. So I think something upwards of 20% of pharmaceutical entities have fluorine in them somewhere. So
well, I'm going to tell my groups that you should do some research on the possible uses of fluorine and whether you need to include that in your considerations.
Yeah, I think that would be the reference that I just mentioned is a good one to read. It's a good review, but yeah, good, excellent stuff. Okay, Michael, are you up next?
Yeah, hi everyone. I'm still here in San Francisco, but I want to introduce my team working on the PLD1 enzyme. They're really doing some great work learning about synthetic biology, but also issues with the supply chain while they try to complete their project. So I believe Anushka is going to kick off the presentation, and please ask questions at the end.
Are my group mates ready?
Yeah, we're ready.
All right. Hello, everyone. We are from Ms. Ramadi's group, and we are working on the project, the development of synthetic aptamers for use as low-cost PLD1 inhibitors by
Anushka Sinha.
Dhruv Pathak,
Alora.
Yeah, and Tech before. Awesome. Okay, so first let's start off with the focus of our project. We're investigating the phosphatidylcholine-specific phospholipase D, or PLD, enzyme that manages signal transduction as well as membrane vesicular trafficking, along with numerous other cellular functions post-hydrolysis of phosphatidylcholine in phosphatidic acid as well as choline. Hydrolysis, by the way, is the chemical breakdown of a compound due to its reaction with water. Phosphatidic acid is a lipid mediator, which is a class of bioactive lipids, that is involved in a diverse set of cellular functions. Choline is a compound involved in the synthesis and transport of lipids. Both are absolutely essential nutrients in the body. In the human body, by the way, there's two isoforms of PLD, PLD1 and PLD2. The one our project is focused on is PLD1, which is a 1074 amino acid sequence, and overexpression of it is linked with cancer, neurodegenerative diseases, cardiovascular diseases, as well as the augmentation of various infectious diseases. So overexpression of PLD1 has also increased inflammation and inhibits apoptosis, which is programmed cell death, leading to the development of cancer. The aim for our project is to find a cheap and novel way to inhibit this overexpression.
Okay, so next I'll elaborate upon the purpose of our project. So a major treatment option for cancer that has been widely used is chemotherapy. And the rough estimate for the total cost of chemotherapy treatment ranges from $10,000 to $200,000, depending on the cancer type, the stage of the cancer, the location of the tumor, the type of drug, and also the number of chemotherapy sessions that is used to treat that cancer. Subcosts also remain a factor to increase the overall chemotherapy treatment cost. However, a major roadblock to chemotherapy treatment is that PLD1 amplifies the anti-apoptotic function and increases inflammation by promoting cancerous cell growth. Thus, more and more cancer patients are now turning towards immunotherapy treatments, in which there have been many recent advances. However, despite these advances, immunotherapy significantly raises treatment costs and increases the probability of inefficient care compared to chemotherapy treatments, which are cheaper. Immunotherapy treatment can cost more than $100,000 per patient, with promising treatments such as CAR-T immunotherapy costing between $375,000 to $475,000. This is before administrative costs and follow-up care. Thus, the purpose of our project is to redirect patients who would otherwise resort to immunotherapy and return them back to chemotherapy treatments by using aptamers to inhibit PLD1 and prevent it from promoting cancer cell proliferation. This also prevents cancer patients from spending an extended amount of fees on immunotherapies, which are more expensive.
I'll talk about the involvement of PLD1 in the signal transduction pathway. So first what happens is that DNA basically transcripts and translates the PLD1 gene into DNA and makes a PLD1 enzyme. And that enzyme breaks down a specific compound called phosphatidylcholine, which then breaks down into two parts, phosphatidic acid and choline. The phosphatidic acid then leaves the cell and then binds to the active site of a tyrosine kinase receptor called mTOR, which is in the cell membrane. And you can see an example in the image there. So basically what mTOR does is it starts a phosphorylation cascade, which is the signal transduction pathway. And the phosphorylation is the signal transduction pathway. And what happens is that different kinases use ATP to transport and sometimes amplify the signal that mTOR started. And then once that signal reaches the centrioles in the cell, mitosis begins.
Okay, so now I'll elaborate on the relevance of PLD1 to mitosis and cell proliferation. PLD activity has been seen to be relatively low in mammals, and it is transiently stimulated upon activation due to the G protein coupled receptor, or the GPCR, which remains at the cell surface. This is shown in the cell signaling pathway image above. GPCRs are involved in multiple mitotic simulations, and they stimulate mitosis by enabling cancer cells to enter interphase. And interphase consists of the G1 phase and the S phase, which are both responsible for cancer cell proliferation, as this is where cell growth and DNA replication takes place. Additionally, the cell that initially had the ability to overexpress PLD1 due to some kind of carcinogenic mutation will continuously conduct mitosis, as the phosphatidyl acid will trigger mTOR repeatedly.
All right, moving on to the relevance of prior research and what has already been done in the field. So really quickly as an overview, we are investigating the effects of PLD1 in cells and finding ways to inhibit the overexpression of PLD1. PLD1's presence has caused cancer cells to show multiple alterations and least effects in cell structure homeostasis as well as signal transduction. According to Tang, Liang, and et al., as the key enzyme implicated in lipid metabolism, which, by the way, is the synthesis of lipids in cells, PLD1 was an overexpression in multiple human cancers, and it was stated to be responsible for aggressive phenotypes such as angiogenesis as well as chemoresistance. Other work has also connected PLD1 with various other diseases, and the work has established a correlation between the overexpression of PLD1 and phenotypic malignancies. ASA has also revealed that PLD1 doesn't specifically cause a type of cancer, but it can lead to a type of cancer. Also, PLD1 treatment is also significantly cheaper than most chemotherapy treatments for cancer, as Alora mentioned previously. Let's look over the image now. So on A, you can see it's a representative immunohistochemical staining of PLD1 in the glioma, ranging from negative, weak, moderate, and strong positive staining. In B, you can see that PLD1 expression was more abundant in cancerous tissues than in paired adjacent tissues in the glioma. In C are basically the overall survival curves based on PLD1 expression in the glioma. You can see that the survival probability decreases if PLD1 was present. Also, the yellow colored part that's around the cancer cells indicated PLD1 staining.
Now let's talk about the inhibition of PLD1. The PLD1 enzyme mediates both hydrolysis and transphosphorylation. Hydrolysis produces phosphatidic acid, which is metabolized by LPP to produce DAG. Phosphatidic acid species are generated downstream of PLC, which is an enzyme. This directly produces DAG. Relation of DAG by DAG kinases produces phosphatidic acid again. This creates a feedback loop. The inhibition of phosphatidic acid is important because phosphatidic acid has been linked to tumorigenesis and malignant invasion. This whole reaction can be stopped either by allosteric inhibitors or competitive inhibitors. The goal of our project is to stop this process as a whole by inhibiting PLD1 directly using a synthetic aptamer, which would be
So why aptamers? So aptamers are basically a really small way of drug delivery, and it has a shorter time frame of being developed compared to competitors. Antibody treatments have also increased a lot of production of inhibitors, and developmental costs are a lot less costly than things like chemotherapy and immunotherapy, as mentioned earlier by Dora.
So moving on to our next steps. First, we want to continue by conducting bacterial transformation using the bacteria DH5 alpha and produce PLD1 in large amounts. Then we would input this PLD1 gene into eukaryotic cells to see the effects of that. Then we would move on to try to find a code for the oligonucleotide chain and lay a framework for synthetic aptamers. Build these synthetic aptamers and start experimenting within that using protein modeling, which is often used in drug design and drug discovery. The end goal is to create these synthetic aptamers, which would be specialized DNA or RNA bases, and they would act as competitive inhibitors, as I mentioned earlier. Later on, we would like to continue by studying binding kinetics and continue our in silico work, most likely bioinformatics studies and so on. So we are incredibly thankful to Mr. Amadi for being a wonderful and patient advisor who helped us understand and execute our project. We would also like to thank the lab techs for ensuring our safety and well-being when conducting labs. Lastly, we are thankful to ASDRP for providing us with the resources and funding to conduct this research project. Thank you all for listening, and please ask us any questions you might have.
Great job, group. This is Mr. Mahdi here. Thank you for presenting. I got a question for you. So why use DH5 alpha?
It's a competent cell that can basically let plasmid or DNA sequences be put into the cell, and then DH5 alpha will basically take the plasmid that we used in bacterial transformations and then make the protein that we want it to.
Thank you. And I think you got some questions in the chat room.
So the thing with aptamers is that they're usually discovered with a process called cell selects. And cell selects, basically, it's kind of like a random generator that gives you DNA sequences. And these DNA sequences are basically analyzed and used to see like how they can work. They're compared against the active site of an enzyme, and then they're used to see how that active site can be inhibited using that kind of random process that it uses to find these DNA sequences.
Michael, congratulations. This is a great slogan. That was a good presentation.
Yeah, no, thank you. Thank you. And I really thank them. This is their first presentation, so it took a while, but they did it. Confidence is key to everybody else who's next.
That's good. No, and aptamers are really hot. This is stuff that, you know, really took off in the last few years in biotech. So it's great that you guys are involved in that. Okay. Any other questions for the Amadi group? Otherwise, we have one more. Oh, we have one in the chat window. I don't know if that was already responded to.
Yeah, I already responded to that.
Okay, great. So I think our final presentation for today is Tyler from my group. Tyler, are you here?
Hey.
So there's Tyler. Tyler joined the group as a junior, working on the development of these antibody drug conjugates for selective and targeted drug delivery for cancer. And Tyler has really grown a lot in the last few months, and Not only learning how to do rigorous synthetic organic chemistry, but also how to work with really sensitive and exceptionally expensive antibodies. So I'm excited to hear today about a summary of some of the progress that we've been making in this project. So it's all yours, Tyler. Go ahead.
Great.
Tyler's
Yeah,
also a Boy Scout. If you guys don't know, he's also a Boy Scout. And has a Land Rover.
that is true. Okay, I'm gonna go ahead and share my screen now. Sorry, hold on. Let's see. All right, is my screen share working?
Sure is, yep.
Great. Okay, so everyone, today I will be talking about the development of next generation pro-drugging strategies and molecular solutions to clinical problems. So one widely implemented form of traditional cancer treatment is chemotherapy. And chemotherapy works by injecting specific drugs into the human body, which then go on to inhibit cancer cells' cell cycles, ultimately preventing its growth. However, this process is not bioorthogonal, meaning the drugs may also affect healthy cells. This is why sometimes we get negative side effects, such as hair loss, fatigue, and loss of appetite. This is why research and more selective targeting is necessary to improve effectiveness of anti-cancer drugs. So an introduction to drug delivery. Selective drug delivery can be accomplished through various means. Small molecule drugs are usually administered intravenously near the area of the tumor. However, technologies such as nanoparticles and ADCs, which I'll talk about later, have been heavily researched as much better alternatives than traditional chemotherapy. So some solutions include antibody drug conjugates and prodrugs. Antibody drug conjugates, or ADCs, are highly selective forms of drug delivery. Specific monoclonal antibodies that bind to cancer cell antigens are joined to a potent drug using a linker molecule. And once that cancer cell recognizes an antibody is binded to its surface antigen, endocytosis results in the payload entering the cancer cell. And then depending on the type of linker we use, a release mechanism cleaves this drug from the antibody, allowing the cytotoxic payload to damage the cell. So similar to ADCs, prodrugs incorporate a molecule onto a potent drug. However, instead of linking this to an antibody, the molecule itself acts as an inactivator to prevent the toxicity of the drug from affecting any cells. And then this inhibitor molecule is synthesized in a way where certain conditions cause its cleavage from the drug, which effectively reactivates it. So by having a controlled release to activate the prodrug, scientists are able to target a specific area of the subject. As the prodrug is a small molecule, it is usually able to diffuse into the cancer cell. Overall, this helps reduce drug cytotoxicity and is also more selective than traditional chemotherapy. So some of the release mechanisms for prodrugs include enzymatic, photoreleasable, and glycosylated prodrugs. Enzymatic release is the most common, where drug is activated through enzymatic cleavage in the target cell. A newly studied mechanism called photoreleasable prodrugs is also very selective, in fact, giving extremely high amounts of selectivity to the person who administers the drug and can be activated at will. Finally, some drugs are glycosylated, meaning a sugar is conjugated to the drug, and the sugar will be cleaved once it enters the cell. So one way to achieve the photoreleasable prodrugs is with the well-studied 2-nitrobenzopyrpectin group. Here's the photorelease mechanism of the 2-nitrobenzyl group upon exposure to UV radiation. I won't be going into the mechanism in depth, but we'll use this technology in prodrugging for our compounds of interest, which I will be going over shortly. So podophyllotoxin. The drug used in our photoreleasable research is podophyllotoxin. Microtubule polymerization, which is a vital process which controls intracellular movement throughout the cell cycle, is inhibited by this drug. Podophyllotoxin is highly toxic and kills cells at a nanomolar concentration range. So we thought it would be a perfect drug to test the photorelease and hope to improve its selectivity. Here you can see one of our prodrugs of podophyllitoxin binding to the active tubulin domain, which we got through computational docking. We synthesized 2 photoreleasable photocages of podophyllitoxin. Oh, sorry. As you can see, simply the substituent on the starting 2 nitrobenzyl alcohol is different, which separates the 2 routes. And then on the very right, you can see the 2 photoreleasable prodrugs of the podophyllitoxin. We also plan on doing cell viability assays to see if our prodrugs will only kill the cells after UV exposure, and also to see if it's more potent than just pure podophyllitoxin. Next, I'll be discussing ADCs. So ADCs, or antibody drug conjugates, are a novel class of immunotherapeutics characterized by a large antibody conjugated to a small molecule drug. Look at the image on the right, and you can see a scale of just how much larger this antibody is compared to a simple small molecule drug, such as aspirin. Our ambition in the subgroup has always been to create a photoreleasable ADC technology, which would not only combine selectivity from controlled release, but also from the monoclonal antibody. However, making an ADC from start to finish with characterization is like building a city. It's incredibly long and it's incredibly challenging. So before we attempted our ambitious goal, we began taking inspiration from actual ADCs. And here are some of the clinically approved ADCs, such as Mylotarg, Adcetris, and Kadcyla. Then I have a more detailed list right here. So now let's talk about MMAE. MMAE, or monomethyl auristatin E, is a small molecule that's highly toxic that mimics a small peptide. It's also a tubulin inhibitor and is extremely toxic to the body. Due to its toxicity, we can't directly administer it to a human body without first conjugating to an antibody. However, many clinically approved ADCs contain MMAE as the payload. So here's how an enzymatically releasable MMAE ADC linker would degrade the cell with an enzyme. First, the ADC would localize at the cell and be uptaken by a lysosome. After the ADC enters the cancer cell, the protease enzymes cleave the benzyl amide and activates a self-immolative mechanism that releases MMAE. The free MMAE payload will then kill the cancer cell from inside the cell membrane. So malignant groups are a vital functional group in the ADCs also. They work by having the malignant group conjugate the linker and the drug to the antibody itself. However, to achieve this reactivity with the antibody, malignants are somewhat unstable in the presence of nucleophilic catalysts. And our lab noticed this when we were synthesizing linkers for our ADC with malignant, because the malignant would decompose when it came into contact with a nucleophilic catalyst, such as DMAP. Hence, we wanted to employ a benchtop NMR study to track the kinetics of malignant decomposition with different nucleophilic catalysts. So we screened 4 nucleophilic catalysts: pyridine, 4-dimethylamminopyridine, or in other words, DMAP, 4-pyrrolidinopyridine, and finally 4-methoxypyridine. First, we added the 4,6-malonyl-hexanoic acid, which is a compound that contains a malignant group. And then we added each nucleophilic catalyst and then monitored the degradation of the malignant with a 1H NMR, UV-vis spectroscopy, and IR spectroscopy. And then our results are as follows. We have graphed the concentration versus time, and we also have UV-vis spectroscopy data to correlate results. And long story short, the more nucleophilic the catalyst gets, the faster the malignant decomposes. Finally, I wanted to talk about SN38. So SN38 is also another small molecule, which is a very toxic drug. And normally we have to conjugate it to an antibody because of its high toxicity. Specifically for SN38, SN38 is toxic because it is a topoisomerase 1 inhibitor. And topoisomerase is just an enzyme that is vital in DNA replication because it helps uncoil DNA strands to prepare it for replication later on. And so far for our ADC efforts for SN38, we've actually been able to synthesize 3 different antibody conjugates of SN38 with 3 different antibodies. And then this diagram shows the linker we made to link it to the antibody itself. And currently, the ADCs are being tested with cell assays at a nearby biotech collaborator. So far, in vivo and in vitro results are pending. Sorry. Yeah, so thanks for having me present our efforts. I would like to thank my fellow group members, Edward, and also our biotech sponsors. If you have any other questions, I'd be happy to answer them now.
Good job, Tyler. That was awesome. That was very good.
Thank you.
Very rigorous. Questions for Tyler? So Tyler, here's the question for you. What was the ugliest experiment that you had to run?
There's a lot of ugly experience we had to run, but I would say the podophyllotoxin project synthesis, especially the unsub route, it was just really hard to synthesize the molecule itself, especially when we had to column it. It was just a really ugly reaction in general. Just very tedious and yeah.
It's like half of chemistry.
It is chemistry, yeah.
So the attendance form is in the chat window. Great work, Tyler, and great work, others. Next Tuesday, we do not have Colloquium because next Wednesday we have a virtual symposium. So join us at that event on Wednesday. But great job, Tyler. And there's the attendance form once again. And that was the last Colloquium of the summer. We'll be back at Colloquium in 2 weeks. And we'll see you all at another ASDRP event. See you all on Saturday, hopefully. Bye. Hey, Michael, are you going to be on site for the meeting tomorrow? Oh, okay. I'll shoot you an email. I think he's already away from his computer.